Hello, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 20. In this lecture, we'll take a second look at circular motion. This topic is covered in Chapter 6 of our textbook by Surway and Jewett. Our goal in this lecture is to develop a deeper understanding of circular motion. To begin with, we should review what we have already learned about circular motion in our previous lectures. If you recall, in our previous lecture on circular motion, we examined in detail the motion of a car driving with a constant speed around a circular track of radius r. So you can imagine that the speed of the car is known, the radius of the track is known, and we were interested back then in knowing exactly what the position or velocity or acceleration of this car was at any given time as it continuously drives around the track. In our previous analysis, we found that the position vector of the car, which we'll denote using lowercase r with an arrow on it, was given by this expression. The x component or the x coordinate of the car is r cosine vt over r, and the y coordinate of the car is r sine vt over r. T is time, r is the radius of the track, and v is the speed of the car. Once you know the position of the car as a function of time, it's easy to calculate the velocity. Remember that velocity is the derivative of the position vector. So we differentiate the x component with respect to t, and we differentiate the y component with respect to t. And what we find is that the x component of velocity is minus v sine, and the y component is v cosine. We can also draw these vectors if we wanted to. We could pick a specific time and plug in numbers into these equations. And if we were to draw these vectors, we would find that the position vectors always point radially, whereas the velocity vectors always point tangentially. In general, circular motion or otherwise, the velocity vector is always tangent to the path that the object is following. In this case, the object is traveling along a circular path, and so these red arrows indicate the tangent lines to that circle. We were also interested in the acceleration of the car. To find the acceleration, we differentiate the velocity. If you took the x component of velocity and took its derivative with respect to t, you would find that the x component of acceleration is minus v squared over r times cosine. And the y component of acceleration is minus v squared over r times sine. Remember that when you take derivatives of sines and cosines, you also have to take the derivative of the argument, so you'll end up with a v over r in addition to the derivative of the sine or the cosine functions. So this is the acceleration vector of the car as it drives around the track. And if we were to actually plug in numbers and draw out these acceleration vectors at several different times, we would find that they always point inwards into the circle, as shown here. These green arrows indicate the acceleration vector. And in the case of uniform circular motion, so constant speed, these vectors always point directly towards the center. We can also calculate the magnitudes of these vectors. It's pretty obvious that the magnitude of the position vector is constant. It's simply the radius of the track. It's pretty obvious that the magnitude of the velocity vectors is constant because the problem begins by saying that the car is driving with a constant speed. Remember that speed is the magnitude of the velocity vector. The magnitude of the acceleration vector is less obvious. The way to calculate the magnitude of the vector is that you take its x component and you square it, you take its y component and you square it, and you add those together and you take the square root. So basically what we're doing is we can imagine this acceleration vector as the hypotenuse of a triangle. We can imagine its x and y components are the adjacent and opposite legs of that triangle, and then we basically apply the Pythagorean theorem to that triangle. And if we do that, we find that the magnitude of this acceleration vector is also constant, and it is simply equal to v squared over r. You might be wondering, where did the cosine go? Where did the sine go? Well, as you apply the Pythagorean theorem to this complicated mess down here, you'll come across cosine squared plus sine squared, and hopefully you remember from your geometry class that cosine squared plus sine squared is equal to 1, so all of that disappears, and you'll end up with v squared over r. So as the car drives around the track, the acceleration vector is not constant. As you can see, the vector points in different directions, but the magnitude of the acceleration vector is constant, and it is equal to v squared over r. On the previous slide, we discussed the motion and the kinematics of circular motion. So we discussed position, velocity, and acceleration. We now want to connect all of that to the forces that are acting on the car or whatever object is engaged in circular motion. Before doing that, remember that we have studied another example of two-dimensional motion. In fact, our first real example of two-dimensional motion was parabolic motion or projectile motion. And when we were discussing projectile motion, we discovered that in order to achieve parabolic or projectile motion, we must have a vertical acceleration of g, where g on Earth is 9.8 meters per second squared. This acceleration was necessary to achieving that particular shape and the various properties of projectile motion that we have discussed. Now that we have learned about Newton's laws of motion, in particular the second law of motion, we know that acceleration and force are related. We know that force is the cause of acceleration and that forces and acceleration can be related through Newton's second law of motion. The net force is equal to mass times acceleration. So if we have a vertical acceleration of g, it's quite logical to ask, where does this acceleration come from? What force causes this acceleration? And in the case of projectile motion, the answer was simple. The force of gravity causes this acceleration. Without gravity, we would not have projectile motion. If you took a cannon into outer space and fired it, the cannonball would not follow a parabolic path. It would just move along a perfectly straight path. So we need this particular force, the force of gravity, to achieve this particular acceleration so that we can then achieve this particular type of motion. We'd like to apply the same logic to circular motion. What we have found is that an object in circular motion must have a radial acceleration of v squared over r, right? We calculated the magnitude of the acceleration vector on the previous slide. We found that it was v squared over r. So henceforth, whenever we observe circular motion, we know that there must be an acceleration of v squared over r in the radial direction. We want to now ask what force causes this acceleration, and the answer can be varied. It turns out in the case of circular motion, this radial acceleration of v squared over r may be caused by one or more forces. It could be any of the forces that we have studied so far or forces that we have not studied so far. So this radial acceleration that's necessary for circular motion can be caused by tension. If we're talking about, for example, a ball tethered to a rope, right, that you're spinning or lassoing over your head, in that case, it's the tension in the rope that is giving the ball this particular acceleration. On the other hand, if you're talking about an object that's moving in a vertical circle, somewhere near the surface of the Earth, it might be weight or the force of gravity that is causing this acceleration. In other cases, for example, a car driving on a track, it might be the force of friction or the normal force that is causing this particular acceleration. So circular motion is a little more complicated because there are a variety of forces that could be responsible for this particular acceleration. In order to have circular motion, it is absolutely necessary to have a radial acceleration of v squared over r. Any force can provide or cause this acceleration Whatever force is responsible in a particular case is referred to as centripetal force. The word centripetal really just means walking towards the center or seeking the center or pointing to the center. So when we speak of a centripetal force, we're really talking about any force that is pointing towards the center of a circle, and more specifically, any force that is providing or causing this radial acceleration of v squared over r. Centripetal force might refer to different specific forces in different situations. For example, if we're talking about a car traveling around a circular road, it might be the force of friction that is the centripetal force. In this case, if we look at the car from the back, we will see that gravity is pulling the car downwards into the road. The normal force is supporting the car, pushing it upwards, perpendicular to the road. And then the force of friction is pointing sideways towards the center of the circular track, and it is the force of friction that is actually responsible for circular motion. More precisely, it's the force of friction between the road and the tires that provides this acceleration of v squared over r. Without the force of friction, this car would not be able to travel along a circular path. If the road suddenly became icy and the friction was eliminated, this car would simply move along a straight path, right? It would veer off the road. It would not be able to maintain its circular motion. In other cases, other forces might serve as the centripetal force. In this example, we have a roller coaster car that is going down and then it's going up. At point A, the car is executing circular motion. I suppose if this were a more exciting roller coaster, we might have a circular loop-de-loop, but it is not necessary to complete a circle in order to have circular motion. This roller coaster car is going to be momentarily traveling along a circular path near the bottom of the track. So at point A, we could say that the car is executing circular motion, and in that case, we would need an acceleration of v squared over r, and the force that is causing this acceleration would be the normal force. So at point A, the normal force from the track is pushing up on the car. The normal force is the force that is actually pointing towards the center. There might be other forces acting on the car, so certainly weight would be pointing down, pulling the car down, but the centripetal force would be the normal force at point A. A second later, the car travels to the top of the track and reaches point B. Once again, we can say that it is momentarily traveling along a circular path, so it's executing circular motion. Once again, we would need an acceleration of v squared over r. We would need a force that is pointing to the center, a center-seeking force. And at point B, it is weight that is acting as the centripetal force. There is still the normal force pointing up, but the normal force is no longer pointing to the center. So notice that in different scenarios, in different situations, different forces point to the center, different forces act as the centripetal force. This acceleration here, v squared over r, is also sometimes known as the centripetal acceleration, although in this course we prefer the term radial acceleration as it is a little more precise and modern. Let's do a practice problem involving centripetal forces. Assuming the skater moves with constant speed, compare magnitude of the normal force to magnitude of weight in each case below. So what we have here is a skateboarder riding his skate on different terrains, basically. Imagine, for example, you're riding your skateboard in a skate park. And to begin with, initially, you are riding your skate on a perfectly flat horizontal surface, and then a second later, you are riding it across a circular path, sort of inside, for example, a half pipe. where the shape of the half pipe is semicircular. And then a second later, imagine that you are riding your skate across a dome. And again, the shape of the dome is perfectly circular in this case. In each one of these scenarios, there are a couple of different forces that are acting on you. Gravity is always pulling down, so there is the weight of the skateboarder. And of course, in each case, the skateboard is in contact with the ground, and so there are contact forces involved here. The perpendicular component of a contact force is referred to as the normal force, and the parallel component is referred to as friction. So in each one of these, we have a normal force, and there might be a little bit of friction as well, although for us in this problem, friction is not that important. We can imagine that the surface is relatively smooth and the wheels of the skateboard are well lubricated so that friction is minimized essentially. So what we're really interested in is the normal force and weight. Now, in previous examples, we've often seen that the normal force and weight are equal in magnitude. In this practice problem, we'll see that that's not always the case. There are situations where the normal force is bigger or less than weight. The situation on the left is the simplest one. The skateboarder is traveling along a perfectly straight path. We can say that his velocity is constant. The speed is constant. We're told that the skateboarder is moving with a constant speed. But what about the direction of velocity? It turns out that's also constant. A second ago, the velocity looked like this, and at this moment, the velocity will look like this, and a second later, the velocity will again look like this. Remember, the velocity is always tangent to the path. And so we can say that the velocity of the skateboarder is constant in time. If the velocity is constant, then we can say that the acceleration of the skateboarder must be zero, because remember, acceleration refers to the change in velocity. A velocity that does not change implies zero acceleration. Now, we're really interested in the y direction because we want to talk about the normal force and weight. We know that weight points straight down, and we also know that the normal force is perpendicular to the surface, so it's going to point straight up. So focusing on the y direction, we can say that the y component of acceleration is zero. And then we recall Newton's second law of motion. Newton's second law of motion tells us that the sum of the forces must equal to mass times acceleration. If we're talking about the y direction, we can say the sum of all the forces in the y direction must equal to mass times acceleration in the y direction. So this is Newton's second law of motion, probably one of the most important equations we learn about in this class. Well, what is the sum of all the forces in the y direction? There are two forces acting on the skateboarder: weight pulling it down, that's mg, or minus mg because it's pointing in the negative y direction. And then there is the normal force. So we can say that the sum of forces in the y direction is n minus mg, or if you want, n plus a negative mg. And that must equal to mass times acceleration. Since we know the acceleration is zero, mass times acceleration becomes zero. And now, if we just rearrange this equation, we find that n is equal to mg. Okay, so this is perhaps not too surprising. This is probably something you already knew, except that now we have proven it in a slightly more formal manner. Before, we would simply say the normal force is a reactive force, it's reacting to weight, but now we can actually use Newton's second law of motion to prove that for this horizontal surface, the normal force is exactly equal to the magnitude of weight. It turns out that's not the case for this middle scenario. In the middle scenario, the skateboarder is traveling along a circular path, at least momentarily he's traveling along a circular path. And if he's traveling along a circular path, we must have a centripetal acceleration. We must have acceleration whose magnitude is v squared over r, and it must be pointing to the center. So if I were to draw the acceleration vector of the skateboarder, I would say it points like this, pointing towards the center of the circle. The magnitude of this vector would be v squared over r. Now we are interested in the y direction, so for now I'm just going to say that the acceleration in the y direction is no longer 0. It's some positive number. We will soon do examples where we will calculate things numerically, but for now let's just say that the acceleration vector in the y direction is not 0, it's some positive number. According to Mr. Newton and his second law, the sum of the forces must equal to mass times acceleration. The sum of the forces, as before, is the normal force plus negative mg, and all of that must equal to mass times acceleration. I don't exactly know what acceleration is here, but I know it's a positive number, so this whole thing must be greater than 0. Right? N minus mg is the net force. The net force is equal to mass times acceleration. If acceleration is not 0, this entire thing cannot be 0. It must be greater than 0. If you now manipulate this inequality, you will find that n is greater than mg. So in this particular case, even without doing any numerical calculations, we know that the normal force must be greater than weight. If I were to draw the forces acting on the person, I would draw one force pointing down, that's weight, and I would draw a larger force pointing straight up, and that would be the normal force. It is necessary for the normal force to be bigger than weight in order for this object to travel along this particular circular path. If the normal force and weight were equal to each other, the object, the skateboarder, would not move along a circular path, it would move along a perfectly flat horizontal path. Let's analyze the third scenario on the right, essentially using the same method. This time the circular path looks like this. This time the center of the circle points is below the skateboarder. Once again, the skateboarder is moving along a circle, so there must be an acceleration. That acceleration is centripetal. It points towards the center. So this time the acceleration vector points downwards because the center is below the skateboarder. So now we would say that the y component of acceleration is a negative number, right? A vector that points downwards in the negative y direction is going to have a negative y component. And therefore, n minus mg this time is going to be less than 0. Because the acceleration is a negative number, we know this must equal to mass times acceleration. Mass, of course, is a positive number, and you multiply it by a negative number, you get a negative number. So n minus mg should be less than 0. And if you bring the mg to the other side of the inequality, you will find that the normal force is now less than mg. So again, we have two forces. Weight, as before, is pulling the person down, but the normal force, which is still pushing the person up, is now much smaller. The normal force has become smaller than weight, and this is again necessary in order for the person to be able to travel along this type of a circular path. So notice that the normal force is quite tricky. It's a reactive force. It's always adjusting itself. It's getting bigger and smaller, depending on the kind of terrain that you're skating on, depending on the path that you're traveling on. In the leftmost case, the normal force is exactly equal to weight, and then as the skateboarder enters the half pipe, the normal force becomes larger, and then as the skateboarder continues onto the dome, the normal force becomes smaller. In all three cases, weight is simply mg. Weight does not change. It's the normal force that is adjusting its magnitude according to the situation at hand. Let's do another practice problem involving forces and circular motion. A Ferris wheel of radius 5 meters turns with a constant period of 180 seconds. Calculate the speed of the Ferris wheel. So we have a Ferris wheel. and each passenger riding this Ferris wheel is going to be executing circular motion. So each one of these passengers is going to be moving basically along the circumference of the Ferris wheel as the entire wheel rotates. So each passenger can be said to be engaged in circular motion. The radius of the Ferris wheel is 5 meters, and the period of rotation is 180 seconds. The period of rotation refers to the time that it takes to complete one rotation or one complete cycle. So if this passenger is at the top at t equals 0, then 180 seconds later or 3 minutes later, the passenger is going to return to the top. Given this information, we want to calculate the speed of the Ferris wheel. The velocity of each one of these passengers is going to be different, but each is going to have the same speed. Notice that the velocity vector of the top passenger is pointing to the right. It's tangent to the circle. If we were talking about this passenger here, the velocity of this passenger would be tangent to the circle as well, pointing like so. The velocity of the passenger here would point like so. In all cases, the velocity vector is tangent to the circle, so pointing in different directions for different passengers, but all of these vectors would have exactly the same magnitude. The speed for each passenger is the same, and it's that speed that we're interested in calculating. Now, if we focus on one passenger, for example, the passenger at the top, we know that this passenger is going to go around the circle once in 180 seconds. The distance that that passenger travels is simply the circumference of the circle, so 2 pi r, and the time it takes for him to travel this distance is 180 seconds. So we can calculate the speed simply by dividing distance by time. Plugging in the numbers, we find that the speed of this passenger is 0.175 meters per second. Now that's the easy part of this problem. Here's a slightly more interesting part. Calculate the normal force acting on a 40 kilogram passenger at the top. So now think about the forces that are acting on this passenger. Obviously there is weight pulling this passenger down. We can calculate weight easily. Remember, the magnitude of weight is simply mg. But of course there must be the normal force acting on this passenger. The passenger is seated and the seat surface is exerting an upward force supporting the passenger. So there should be a normal force that also points upwards. What we're interested in is calculating the magnitude of the normal force. You might be tempted to say, well, the normal force is reacting to weight, so they must have equal magnitudes. However, as we saw in our previous practice problem, that's not always the case, especially when things move along circular paths. So we have to be a little more careful and analyze these forces more rigorously. To do that, we'll use Newton's second law of motion, F equals ma. However, as you remember from our previous lectures on circular motion, it is always beneficial to use the radial tangential coordinate system for circular motion. Here we're talking about the circular motion of a passenger, so rather than using the traditional standard XY coordinate system, we're going to use the RT coordinate system, the radial tangential coordinate system that moves with the object around a circle. In that coordinate system, Newton's second law of motion looks like this. The sum of the forces in the radial direction is equal to mass times acceleration in the radial direction. What are the forces in the radial direction? Well, we have two forces, N and W. You can see both of them are pointing along the radius of the circle. So we're going to say that the sum of the forces is the radial component of the normal force plus the radial component of weight, and that must equal to mass times acceleration in the radial direction. We can also note the fact that weight has a magnitude of mg and it points downwards. More precisely, it points into the circle towards the center. Remember that in the radial tangential coordinate system, when a force points out of the circle is positive, when a force points into the circle is negative. So we can write n rad simply as n, and we'll write W rad as minus mg. So the magnitude is mg, and the negative sign comes from the fact that weight points towards the center of the circle. The mass remains as mass, and we're going to now remember that for circular motion, we must have a radial acceleration of minus v squared over r. You can say the magnitude of the acceleration is v squared over r, but we remember that the acceleration must point inwards towards the center, so that's going to be a minus acceleration. We now have a nice equation that we can solve for n. We already know what m is, we know g is 9.8, and we have figured out v, the speed of the passenger, and the radius is given to us. So we can say that the normal force is equal to mg minus mv squared over r. Plugging in numbers, we find that the normal force on the passenger at the top is going to be approximately 391.7 newtons. Let's continue this practice problem one step further. Same Ferris wheel moving with the same speed. Part C asks us to calculate the normal force acting on a 40 kilogram passenger at the bottom of the Ferris wheel. So now we're focusing on the passenger near the bottom of the Ferris wheel. Again, two forces are acting on this passenger. Gravity, or planet Earth, is pulling the passenger down. We call that force weight. And the contact between the passenger and the seat creates the normal force. That's the force that's basically supporting the passenger. The normal force points upwards in this case. Again, we're interested in calculating the magnitude of the normal force. To do that, we begin with Newton's second law of motion. Notice we're not using an XY coordinate system. Here we're talking about an RT coordinate system, and more specifically, I'm focusing on the R component, or the radial component. As before, there are only two forces, so N rad plus W rad is equal to MA rad. We notice that the normal force is now pointing inwards, is pointing to the center of the circle, so it's now a negative force in our radial tangential coordinate system. And notice that now weight is pointing away from the center. Whenever a vector points away from the center, it's considered in the positive direction. That's the convention for radial tangential coordinates. So this second line can now be written as minus n. The normal force is negative because it points to the center, and plus mg, weight is positive because it points away from the center. And the acceleration, the radial acceleration, will be pointing towards the center no matter where we are along the circle. So it will always be minus v squared over r for any one of these passengers. So now we can solve this equation for n. We find that n is equal to mg plus mv squared over r. Recall that for part B, this expression was mg minus mv squared over r. Now it's plus mv squared over r. And if we plug in the numbers, we find that the normal force is approximately 392 newtons. It's interesting to compare part B and part C of this problem. We found in part B that the normal force on a passenger at the top is approximately 391, but when that same passenger comes to the bottom of the Ferris wheel, the normal force becomes a little bit larger. It becomes 392 newtons. This change in the normal force is responsible for the feeling you sometimes get on a Ferris wheel or a roller coaster of weightlessness. You may have noticed that on a Ferris wheel, especially a fast spinning Ferris wheel, you feel a little bit weightless near the top and you feel a little bit heavier near the bottom. The same thing happens on a roller coaster. The same thing happens in elevators that accelerate rapidly. And that feeling of weight that you get is related to the normal force. Your weight is not changing, your weight is mg the whole time, but your sensation of heaviness is related to the normal force. When the normal force is large, you feel like you're being pressed into the ground, so you feel heavier. And when the normal force is small, you feel like you're being lifted off the ground, so you feel a little bit weightless. Here, the difference between the two normal forces is not that big, but if this were a Ferris wheel that was rotating much more rapidly, you would notice that the difference between the two normal forces at the top and the bottom would be more pronounced. Let's finish this lecture with a brief discussion of coordinate systems. You probably noticed in the previous practice problem, I did not use a standard XY coordinate system. It turns out when it comes to circular motion, it is always to your advantage to use an RT or radial tangential coordinate system. In this coordinate system, the R-axis is always pointing along the radius of the circle, wherever the object of interest is, and the T-axis is always pointing tangentially to the circle. The R-axis is pointing in the positive direction when you move away from the center, and the negative direction when you move towards the center. The T-axis is positive when moving in the counterclockwise direction and negative when moving in the clockwise direction. These conventions might make problems like the Ferris wheel problem that we were just discussing a little confusing. If you remember, we were analyzing the forces acting on a passenger near the top of the Ferris wheel and a passenger near the bottom of the Ferris wheel. If you're using a standard XY coordinate system, then all the forces are pointing in the Y direction. And at the very top, we would say that the normal force is positive Y and weight is pointing in the negative Y. And the same thing happens at the bottom of the Ferris wheel. Normal force is again positive and weight is again negative. So the XY coordinate system is pretty consistent. The positive Y direction is always the same direction, always pointing upwards. The radial tangential coordinate system is a little more confusing. At the top, we would say the normal force is pointing in the positive direction because it's pointing away from the center, but at the bottom, the same force, the normal force, would be said to be a negative force because now it's pointing towards the center as opposed to away from the center. So using the RT coordinate system requires a little more care because what is positive and what is negative can change a little bit depending on which part of the circle you are using. However, the RT coordinate system has the immense advantage of giving us the acceleration quite simply as minus v squared over r. In the RT coordinate system, we can always say that the radial acceleration is minus v squared over r. However, we do not have that advantage in the XY coordinate system. And that's the end of this lecture. Thank you for your attention.